All right, let's just dive right in. Today, we're going to cackle one of the most fundamental, and let's be honest, one of the absolute weirdest ideas in all of modern science, the quantum. So I want you to think about this question, because it's a big one. Is the universe smooth or is it chunky? I know, it sounds a little strange, but this exact question completely shattered the world of physics a little over 100 years ago. For the longest time, physicists were convinced that nature was smooth. Think about it like a ramp, right? You can stand anywhere you want on it. Energy could be any value, big or small. But there was this one nagging problem that just wouldn't go away, and it revealed that reality, deep down, isn't a ramp at all. It's much more like a staircase. You can be on this step, or you can be on the next one, but you can never, ever be in between. Okay, so let's set the scene. We're going to rewind to the late 19th century. And at that time, physicists, well, they felt like they were pretty much done. They really thought they had the universe all figured out. It was this elegant, complete, and totally predictable clockwork machine. And this was their classical worldview. The idea was that energy wasn't made of stuff. It was just a continuous quantity you could divide forever. Light and heat just flowed seamlessly, kind of like water in a river. Everything just made perfect, logical sense. But that beautiful, orderly picture of how the universe worked, it was about to be completely shattered. And it was all because of a very simple question that classical physics had no answer for. Scientists were trying to understand the glow that things give off when they get hot, what they called black body radiation. Just picture a piece of metal in a forge, glowing red, then yellow, then white hot. They just wanted to predict the exact colors of light it would emit. Simple enough, right? And when they measured it in their labs, the results were always the same. As you can see here, the energy hits a peak in the visible light spectrum, and then it just gracefully drops off in the higher frequency ultraviolet light. This is what actually happens in the real world. But when they used their trusted old-school classical theories to calculate this, the math gave them a result that was completely absurd. It predicted that any hot object should be blasting out an infinite amount of energy as ultraviolet light. Yeah, infinity. This massive failure got a fitting nickname, the ultraviolet catastrophe, and it was a huge warning sign that something was deeply, deeply wrong with physics. So physics is broken. Then, in the year 1900, a German physicist named Max Planck comes along with an idea so radical that he barely even believed it himself. It was pretty much a desperate guess just to make the math work. He made this wild suggestion. He said, what if energy isn't a continuous flow? What if it's only emitted and absorbed in tiny individual packets? Not a ramp, but a staircase. And this is his famous formula, E equals h nu. All it says is that the energy E of one of these packets is just its frequency nu times a new fundamental number h, which we now call Planck's constant. This was the recipe for a single packet of energy. Planck called these little energy packets quanta. And with that one revolutionary idea, the equations suddenly matched the experiments perfectly. The ultraviolet catastrophe, it just vanished. The staircase model of reality actually worked. Now, for a few years, most physicists, and that includes Planck himself, they just thought this was some kind of weird mathematical trick, a convenient fiction to solve one pesky problem. But then, a young patent clerk you might have heard of named Albert Einstein, he took it seriously. Einstein realized that Planck's quantum idea could perfectly explain another nagging mystery called the photoelectric effect. That's just when light shining on a piece of metal can actually knock electrons loose. So Einstein proposed that light itself isn't just a wave, it's actually made of these little energy packets. So here's how it works. Think of light as a stream of tiny bullets, or quanta, which we later started calling photons. Each photon carries a specific amount of energy based on Planck's formula. When a photon smacks into an electron, it transfers all its energy. But here's the kicker. If the photon doesn't have enough energy, nothing happens. It's a total all-or-nothing deal. And that proved it. Light energy comes in chunks. Quanta were real. And this one bizarre idea, that energy comes in chunks, it didn't just fix a couple of niche problems in physics. It ignited a revolution that is directly responsible for the world we are all living in today. And make no mistake, understanding the quantum world wasn't just some academic exercise. It gave us the power to manipulate matter at the atomic level. And that led directly to lasers, to transistors, and to the microchips that power every single piece of modern electronics, from the computer you're on to the smartphone in your pocket. It turns out, everything is quantum. The reason atoms are stable and don't just collapse on themselves, the way the sun generates light, the very chemistry that makes life possible. It all depends on energy and other properties only being allowed to exist in these specific, discrete, quantized steps. The universe is chunky. So we went from this little crack in 19th century physics all the way to the absolute foundation of our digital age. The discovery of the quantum just shows how one truly strange idea can completely reshape how we see everything. And it really makes you wonder, what's the next quantum leap going to reveal?